In this video, I'm going to go through another problem using implicit differentiation, very similar to the first, slight twist though. Here I'm going to find the tangent line to the circle x squared plus y squared equal 1 at the point 1, 0. You'll notice if I take the coordinates 1, 0 and I plug them in, I get 1 squared plus 0, and that is equal to 1. So this point is on the circle. And now how do we find the tangent line at that point? Now if you draw the circle and look at it, you may just be able to figure it out, but I want to go through this formally because you won't always be able to easily draw the shape. And so I want you to see the general principle of how you would do a problem like this. Okay, now I am going to draw the circle and kind of intuit what the answer is just to motivate the thing that I'm going to do here. And that is we're right at this edge of the circle. That's the point 1, 0. And the tangent line right here is dead vertical. And so what's the problem with that? I could just write down right now that the tangent line I'm looking for has formula x equal 1, but that's only because I was able to do this. So I'm going to only half use this picture and then use that to motivate the method that I'm going to show you for any kind of problem where you might not be able to draw this picture as easily. So the problem here is in the last video where I was just looking for a tangent line that had a slope of 1, what we did was we assumed that y was a function of x, and we rewrote the relationship between x and y like this, and necessarily we couldn't include the whole circle here, but in the end we found two separate points. One was on the upper half circle and one was on the bottom. So because it ended up separating into two answers, we were able to find both possible answers, even though we initially just assumed that y is a function of x, which means that we were just looking at, let's say, a piece here, or really any answer all the way across here would work, or any answer all the way across here would work. Now, what's the problem with making this assumption in this case? The problem is that right at this point, the circle does not satisfy the same property. In other words, no matter how small a little interval you consider around this point, you'll never have y being a function of x because there's a little piece below and a little piece above. And if we were really close, then we could just pay attention to the piece above. But right at the point, there's no way we could think of that as a function. And we can't take derivatives leading into that point because we have this problem of an infinite slope there. So what's the solution to this? Well, when I said y is a function of x, I was just appealing to this tradition of always assuming that the y values are a function of the x values. And there's no reason to do that except that you learned how to do that in high school, and for decades or hundreds of years people have tended to use x and y in particular ways. Instead, I'm just going to go a little crazy here and say I'm going to assume that x is a function of y. And so really what I'm doing is I'm saying, like, let's redraw this whole picture instead of putting it this way. And I only do this because we tend to feel that the function should be in the vertical direction. So let's see, can I do this? Is it going to let me? No, it doesn't let me. Okay, so it's a little bit rotated, but we're basically doing this. We're looking at it on the side. And so I'm going to have this relation now expressed with x as a function of y. And now at this step, I'm going to take the derivative of both sides with respect to y. So I will take the derivative on this side of x of y squared plus y squared, and on this side I'll take the derivative with respect to y of 1. So here again we have a chain rule because we're taking a derivative with respect to y, so there's an outer function which is thing all squared, and the thing itself is a function that's been plugged into the squared, so that's my inner function. And so what I end up with here is I end up with the derivative of x with respect to y. So that's the x dy. And I have to evaluate it at y. And then I multiply that by x. Whoops, nope, sorry. Got that backwards. So let's do that again. So this is going to be 2 times x of y. That's the derivative of x squared with x of y plugged into it. And then we multiply that by the derivative of x with respect to y. I could write that as d dy, but because y is the only argument there, it's clear that prime refers to a derivative with respect to y. And then I add 2 times y, and now I need no chain rule because y is the independent variable with which we're taking the derivative. And then on this side, I get 0 because the constant function has a derivative of 0. Okay, so now, now if I want to find the slope of the tangent line at that point, that's hiding right here. The x and y value, I'm actually given those. So I could solve for x prime equal right now, and then I'd have a general expression. Well, I guess I can do that, it doesn't hurt. So if I solve for x prime of y, I'll get a minus 2y by bringing this over to the other side, or subtracting 2y from both sides. And then I'm going to divide by the 2x of y. And I end up with minus y over x of y. And in this particular case, the y value is 0 and the x value is 1. And here there's no mystery about what the slope is. It's not infinite or undefined. It's actually just equal to 0. So now if I want to write down the general form of tangent line, it's, remember now I'm thinking of x as being the function and y as the independent variable. So the expression for the tangent line will be x equal, and now I have a slope which is change in x over change in y, which is x prime, multiplied by y is the independent variable, so it's y minus y0, plus the function value, which is x naught now. And plugging in these pieces, I get a 0 here, multiplied by y minus 0, plus 1. And so that is the equation x equal 1, which, if you remember early on, I sort of just intuited that from this picture here, but now we've actually found a way of solving it in general. And so for other functions where you're trying to find a tangent line at an infinitely steep spot, this would be the way that you could do it without ending up with infinities cropping up in your calculations. Okay, I will end there, and I will post another video after this going on with more uses of implicit differentiation.